Hello, Hafide, and aloha once again. Thank you all for joining us again today. Welcome to the second webinar of the Pacific Desk 2022 webinar series. I am David Hitzel, the Pacific Desk Guam instructor, and today's topic of discussion is undersea volcanology, tsunamis, and prediction of future volcanic eruptions. The usual reminders before we begin: this is being recorded for educational and documentational purposes and will be posted simultaneously on Facebook Live. Please leave any questions in the comment sections and include your location and affiliation. Questions can also be asked through Facebook Live if you prefer that route. A period of oral questioning will be allowed at the end of each talk, but otherwise please refrain from having your video or audio switched on. And then lastly, the video recording will be saved to view later on Facebook, and I will also be posting it on YouTube. Okay, so upcoming webinars. The next webinar will be on the topic of application of the NOAA Unique Combined Atmospheric Processing System, otherwise known as NUCAPS. So this will be presented by Brandon Idlet from the Weather Service in Guam. NUCAPS is one of the newer forecasting tools that's available. It blends IR and microwave satellite data, and then it funnels it through an algorithm to produce soundings of the atmosphere. So it's particularly useful for estimating moisture and instability over regions of the globe where radiosonde data is limited or lacking, such as the tropical Pacific. So that'll be mid-April, and then looking at doing one on global sea level rise for May. Okay, so today's speakers, they're all affiliated with the Hawaiian Volcano Observatory. Our first speaker, Drew Downs. Drew was born and raised in Central Illinois and received his Bachelor's of Science and Master's of Science in Geology from Southern Illinois University. He, after that, went to New Zealand for his PhD, which he obtained from the University of Auckland while working on large caldera forming eruptions from the Taupo volcanic zone. He then worked for 6 years at the California Volcano Observatory with a focus on volcanism within Northern California and Saudi Arabia. And then he moved to Hawaii in 2020 to work at the Hawaiian Volcano Observatory as a research geologist, where his primary work concerns geologic mapping, geochemistry, and geochronology of the summit of and southwest rift zone of Kilauea. Our second speaker is Natalia Delling. She is a research geologist specializing in volcanic hazards and their consequences. She received a Bachelor's of Science in Geology from Caltech, a Master's by Research in the Science of Natural Hazards from the University of Bristol, and a PhD in Geology from the University of Oregon. Prior to her current role, she spent 8 years at GNS Science in New Zealand as a volcanologist. In that capacity, she was an observer at the conjoint WMO Volcanic Ash Advisory Center Best Practices Workshop and WMO IUGG Volcanic Ash Scientific Advisory Group meeting in New Zealand. She also was deployed by the New Zealand Ministry of Foreign Affairs to provide support to the Vanuatu Meteorology and Geohazards Department in April 2018 during the Ambe eruption. And our last speaker is Art Jolly. He is a research geophysicist with interest in seismology and aeroacoustics of volcanoes. His research is focused on the indicators of unrest at volcanoes before an eruption has occurred and consequent hazards during and after eruptive activity. He has worked as a seismic analyst in Alaska and researched the seismicity of the Katmai Group volcanoes, the Soufriere Hills volcano in Montserrat, and volcanoes in the South Pacific, including Wukari in New Zealand and Ambe in Vanuatu. He is currently a monitoring and research scientist at the Hawaiian Volcano Observatory, where his primary interests are characterizing eruptions, understanding the energetics of post-eruption events, including pyroclastic, effusive, and explosive eruptions. Art obtained his Bachelor's of Science in Geology from Central Washington University, Master's of Science in Geology from the University of Montana, and PhD in Geophysics from the University of Alaska at Fairbanks. Okay, and then just a brief word on the Hawaiian Volcano Observatory. They're part of the US Geological Survey's Volcano Hazards Program. I believe there's 5 observatories associated with them. They monitor, investigate, and assess hazards from active volcanoes and earthquakes in Hawaii, and issue warnings and advance scientific understanding in order to reduce impacts of volcanic eruptions. And they do education of the public as a large part of their job. Their original office was located on the rim of the Kilauea caldera, but it was moved to Hilo in 2018 when explosions and violent earthquakes accompanying the onset of a partial summit collapse occurred in the vicinity of the building. Their current monitoring network includes 200 sensors on the Big Island, functioning 24 hours a day and under the watch of 30 scientists and specialists in the fields of geology, geophysics, seismology, volcanic gases, and others. Okay, and then my brief comment here on the, so this webinar was prompted, of course, by the recent Tonga eruption. And my thoughts on the Tonga eruption was when I saw the very impressive satellite images, my first thought, of course, was, is everybody okay? But my second thought was, well, how does this compare to Krakatoa? So I thought I would briefly introduce Krakatoa, because if you're an earth science person in any field in earth science, you should know about Krakatoa. And then it also either still betters the Tonga eruption or it definitely rivals it. So the Krakatoa eruption I'm talking about occurred in 1883. Krakatoa was a volcano that was right between the islands of Sumatra and Java in Indonesia. And it's actually most famous, this eruption, for generating the loudest sound in recorded history. So the explosion registered 170 decibels at 100 miles from the source and was heard several thousand kilometers away in Australia and in the Western Indian Ocean. So the sound was so powerful, it burst the eardrums of sailors floating 70 kilometers away from the eruption site. The sound wave from the blast circled the world 7 times within the following 5 days, and the shock wave was recorded by barographs on the other side of the globe. The main eruption, as well as previous and subsequent eruptions, generated tsunamis. The tsunami from the main eruption destroyed hundreds of villages and low-lying regions of Indonesia and was responsible for many of the 36,000 deaths associated with the eruption. And many of the other deaths were related to the pyroclastic flows, which are superheated steam and ash, which traveled across the sea, hitting nearby islands. So the dissipating ash cloud actually blanketed the Earth, causing a global cooling over the course of the next year and made for strange and fiery sunsets worldwide. These sunsets are said to have inspired the Norwegian painter Edvard Munch to produce his famous painting, The Scream. Munch is quoted as saying he was inspired to paint it after feeling a great unending scream piercing through nature. The eruption took most of the island of Krakatoa with it, as well as some neighboring islands, with the caldera collapsing into the sea. And what was left of the island reemerged as Anak Krakatoa, or Baby Krakatoa, in the early 20th century, and it remains a threat to this region to this day. So I wanted to bring this up because the comparisons here with the Tonga eruption are obvious. Both were monumental explosive eruptions. Both sent measurable sound pressure waves around the world. Both yielded major tsunamis, which wreaked havoc over considerable distances. Both yielded massive soaring ash clouds, which impacted large regions of the Earth's surface, and both annihilated the islands on which the volcano was a part. Okay, and so with that brief introduction, I will turn it over to our very knowledgeable speakers.
All right, I guess I am up first. My name's Drew, and let me see if I can share my screen here.
Yep.
Oh, success. Can everyone see my screen?
Yes.
All right, perfect. That seems to work a lot easier than it normally does. So yes, I'm Drew Downs. I work at the Hawaiian Volcano Observatory, and I'll be going first with just a laughably brief overview of submarine volcanism. So I've tried to take what's normally kind of a semester-long course and condense it down into the next 15 to 20 minutes. of what is submarine volcanism, what sorts of features can we see, and just kind of let Natalia and Art go from there as far as what are the hazards and then what went on at Tonga. So I'm not going to talk about the eruption earlier this year of Tonga at all. In fact, this photo that I have on the introductory slide here is the only photo I've got from any volcanism in Tonga altogether. And this is from 2009. You can see the emergence of a submarine volcano above the waves here. You've got at the bottom here, you've got your basal cloud, and you've got your kind of cocktail pumice coming back down, falling to Earth. That's not to say that we won't be discussing other things in this region, particularly around Samoa, American Samoa, and other parts of the Tonga chromatic arc. So just as a brief overview to get everyone on the same page, where do volcanoes occur? Well, as most of us know, we are sitting on top of plates that are kind of floating on top of the mantle. These are called tectonic plates. And there's really three types of plate boundaries. There's convergent, where two plates hit each other, divergent, where two plates pull apart, and transform, where they slide laterally past one another. So we get volcanism mainly at two of these different types of plates. Convergent plates are where two of these plates hit each other, and the heavier one, usually the oceanic plate, starts to subduct or go underneath the continental plate. You also can get oceanic to oceanic subduction as well. In these cases, you get volcanism that forms arcs. So you can think of the American West, the Cascades Arc, or the Aleutian Arc in Alaska or Indonesia. You can also think of Tonga. That would be, in this case, an oceanic plate subducting under another oceanic plate. In this case, you get an island arc instead of a continental arc. You also get areas where the crust is pulling apart. And as you're pulling apart, you're thinning the crust, makes it easier for the mantle to fill in, undergo decompression, melting, and you get volcanism there. Now, again, this happens in both oceanic and continental settings. And some of the best are, say, the mid-ocean ridges of the mid-Atlantic, and up near Iceland, this is where you get continental versions of that. The same is true for the East African Rift, where Africa is slowly pulling itself apart, and over millions of years, it will actually start to form a sea floor. So even though you're getting continental spreading, eventually that's going to turn into oceanic spreading if it goes on long enough. Now, transform boundaries themselves, they can have minor volcanism associated with them where they get pull apart basins, but you can think of a transform boundary like the San Andreas Fault, and for the most part, they do not get any volcanism associated with them. The other big area that tends to have volcanism are hotspots. And again, we get these both in continental and oceanic settings, with the big continental one that's typically cited being Yellowstone, whereas an oceanic setting hotspot, you can think of Hawaii, where it's got this long track of seamounts that eventually leads to the Hawaiian Islands, which are still above the waves. So those are our main areas where we get volcanism. So moving on and just looking at kind of over the past 5 years, historically active volcanoes, which was nicely put together here by Ruben and others. And some of you may know Ruben at the University of Hawaii. And you can see here kind of what we've got is we've got subaerial volcanoes, we've got shallow submarine eruptions, and we've got deep submarine eruptions. Looking at this image up here, you can see the white lines kind of represent these tectonic boundaries. And the yellow far outnumbers the blue and the red. And you can see they follow some of these lines. They don't overlap, but they come down the west coast or up through Alaska, down the west coast of Americas, and also over through Indonesia, the Philippines, Japan, and up through the tip of Russia, as well as other places. These are those subduction settings. So these are continental arcs for the most part. You can see they far outweigh some of these reds, which do sit on these spreading ridges out here in the middle of the ocean, as well as the blues, which are shallow submarine. Well, this is because over the past 500 years, of course, subaerial eruptions are easier to spot. Submarine eruptions are very poorly represented in the record just because the ocean floor is not as well explored as the continents. You can see down here, kind of in the pie graphs, even though we've got a lot more spreading ridges here, they have very few dots on them representing eruptions, even though our spreading ridges actually produce most of our volcanic output throughout the year. And it's just well known that it's harder to quantify what's going on in the ocean than on land. And that's all that this is trying to represent. So why is submarine volcanism important? Well, going back to that previous image, we can just highlight here as an estimated percent of global volcanism, only 15% is suggested to be subaerial, whereas 85% is subaqueous, so submarine volcanism for the most part. And if we go down here, you can see of the explosive eruptions of that 85%, and this is highlighted as pessimistic at best, maybe 4% of all eruptions are explosive subaqueous ones, whereas for the subaerial, maybe 12% of that 80, and that's being generous, are explosive eruptions. So here's our hypothetical volcano, and this is just one of several volcanoes that we can get. They come in many types and varieties, and you'll notice this is a subaerial volcano, but they tend to act like submarine volcanoes in a lot of ways. Some of the terminology is different, some of the wording is different, some of the processes can be different as well, but they tend to have very similar processes that form their magmas and during their eruptions. So this is just an image of a typical arc volcano that you would see in the US Cascades or in Indonesia or Japan. So you can see coming out the top during an explosive eruption, you can get this eruption column. You can get the same thing in submarine eruptions. Typically it'd be called a gas jet. You can also get domes that form on the side and cause collapses. You can get landslides and debris flows. You can get lava flows. A big one that's always mentioned are pillow lavas. These are just very slow flowing lava flows that cool very quickly. But you can also get pyroclastic flows and hydrothermal features, such as the black smokers that are famous at mid-ocean ridges. You can also get shield volcanoes. So this is an image of a shield volcano. So basically, take the island of Hawaii, Mauna Loa, Kilauea, and stick it underwater, which is exactly where these volcanoes come from. We even have our own seamount offshore of Hawaii, which I'm going to go ahead and call Loihi. It's actually got a new name now that I can never remember. But off the island of Hawaii is a seamount called Loihi that'll eventually emerge from the waves as a shield volcano. And once it dies, it'll submerge back below the waves. But again, you get a lot of these same features. You can get calderas in submarine volcanoes, along with rift zones and different low bait and sheet flow lava flows with breakouts on them. So let's just take a look at our different types of submarine volcanoes and where they're located. And I'm just going to break these down into two classes, really, mid-ocean ridges and seamounts. And mid-ocean ridges, as you can guess, align along ridges in the ocean. So these are the divergent boundaries. This is where the crust of the ocean is being pulled apart. And you can see here on this map, these are in black, and these red circles are kind of the axis of the seamount, or I'm sorry, of the ridge, with the length of the line kind of its spreading rate. And the spreading rate actually has a lot to do with what the ridge is going to look like. So even though these are called mid-ocean ridges, some of them in their middle are actually deep troughs. And it's well known that the faster the spreading ridge, such as the East Pacific rise, the faster it rifts apart, you will actually get a ridge in the middle. As you start to slow down, this ridge is less prominent. And once you're at a slow spreading ridge, say the mid-Atlantic ridge, you actually get a deep trough on the side of two separate ridges. Same with the ultra slow spreading ridges. So your fast ridges have kind of this axial high, and your slow spreading ridges have deep valleys to them. And this is just kind of some sonar mapping of the ocean floor and what some of these look like. So the East Pacific rise here is on the far left, and you can see it does have this high spot in the middle of it that kind of tapers off as you go off down to either side. Our mid-Atlantic ridge here in the middle is got that deep valley in the middle of it, and then it's high on both sides. The same with our ultra slow spreading ridge. So the Southwest Indian Ridge on the right-hand side, it's got an even deeper valley in the middle of those two ridges. The other volcanic features are usually our volcanic seamounts. And these are usually based on hotspots or island arcs that have not risen above the waves yet. And as you can see on this map, this is a map from Stalgil and Coppers that show the distribution of seamounts greater than 1.5 kilometers tall based on echo sounding locations. So you can see there are a lot of seamounts in the ocean. Now, does that mean there's a lot of volcanoes out there that are active? No, only a fraction of these will actually be active, but it has shown just how active in the past that particularly the Pacific Ocean that you can see quite well here has been. So just kind of the history of volcanic seamounts, and you can kind of think of this as the history of Hawaii as well, is when you're first starting off, your hotspot's coming up, you're getting your magma welling up, you're getting a little volcano form. So you're getting just this little patch of lava that's starting to build itself up. And you can see in number 2 there, it starts to build itself up even more until you start getting a more differentiated magma chamber, a more complex system. Sometimes, and not always, these can form calderas at the top. So anyone who's familiar with Kilauea or Mauna Loa would know that they've got this caldera at the top of them where a lot of eruptions occur. So a lot of seamounts under the waves, of course, can have these as well. Once you start to break the surface, at least in tropical climates, you might get a reef associated with it. And that's where we're at with Hawaii now. We've got reefs on part of the island. We've got calderas at the top. We've got lava flows, volcaniclastics. Eventually, this hotspot, well, the plate is actually moving over the hotspot, so the hotspot stays still, but it'll no longer be feeding magma into that system. And so eventually, the weight of this volcano and erosion are going to start to wear it down until it's below the sea again. And you can see over here and kind of the image off to the right that we've got our active volcano. It's now died, it's sinking, it's got a fringing reef, it's got an atoll, and soon it's below the waves. And eventually, because it is oceanic crust, and oceanic crust does not stick around forever, it will eventually get subducted into, well, a subduction zone itself. So here's just some other examples of volcanic seamounts themselves, and you can see how big the variety is of the morphologies here. So here you can see the Hussey guy out and Hosea guy out, a humpback seamount here. Here you can see one that's just labeled with latitude and longitude, but it's got rift zones coming off of it, just like Kilauea and Mauna Loa do. Here you can see in American Samoa Wailu'u volcano, and here's another close-up with a resurgent cone that's coming out of its caldera, as well as these over in the axial seamounts with a caldera at the top and the Banff seamount with several calderas in these kind of squat features, as well as Brothers Volcano here with a post-caldera lava flow or dome coming out the top, which is similar to things that you'd see in, say, Mount St. Helens, which collapsed and then had this post-lava dome that came up a couple decades later. So those are just some of the morphologies that you can see. They come in all shapes and sizes. So what do their eruptions look like? Well, typically, a lot of people hear of pillow lavas, and you can see down here in American Samoa, the Nafanu resurgent dome in the middle of a seamount, which has these pillow lavas. And this is just rapidly cooled lava once it encounters water. It doesn't flow very far, it just kind of creeps along. But you can see over here on the left-hand side, as we increase our flow rate, we go from pillows to more low bait structures to more of a sheet flow. So the Mid-Atlantic Ridge is well known for having pillow lavas, but once you start getting faster and faster extension rates, you start getting more low bait and sheet flow type morphologies. And you can see down here along the bottom, the difference in kind of morphology. The Mid-Atlantic Ridge here is quite, stippled, broken up. It's got highs and lows all over the place, where it's a much smoother topography for the East Pacific Rise there. But there's also explosive eruptions as well. So these are from kind of the Marianas Arc over by the West Pacific. And you can see here, you've got this gas jetting, this ash plumes, but it's also picking up these larger rocks that it's pulling out as well. You can even see in this panel C right here, this orange tinge to it, which is a mix of sulfur and ash. So these are the same types of gases that will be coming out in a subaerial eruption as well. You're getting water vapor, you're getting CO2, you're getting sulfur and other exhaled gases that are coming out. You can see over here on the right some other great examples of this from the Marianas and the Lau Basin, where you've got kind of these bubbles of lava forming that pop, so almost like Strombolian eruptions, but also these gas jets of ash, gas, and larger debris coming out in these explosive eruptions. So one of the more impressive one of these occurred in from the Havre Seamount in 2012. And you can see, even though this is well below the waves, well, you can't see that, but take my word for it, it's well below the waves. You can sometimes, when these eruptions happen, you get pumice that comes all the way up to the surface and makes these rafts. So you can see highlighted in yellow over here in 2012, NASA satellite imagery of this kind of tan colored string right here, which is actually just a bunch of pumice that came out of an explosive eruption. And pumice tends to be light. It's got a lot of vesicles to it, so it holds a lot of vapors and other gases. So it makes it light, it makes it float. So you can see in the bottom image as well that it's kind of cloud covered, but you can see kind of the plume here, the ash stained water, as well as the pumice raft. And these can be hazardous to blocking intake valves from different ships that go through these areas. And they can persist for a long time. So you can actually see in this top right panel here is actually the green on this figure here from July 4th. And they've kind of mapped out how long it took this to dissipate, not fully, but you can see it goes on to the 30th of July here in red, then August 3rd. They've mapped it drifting through different parts of the region. So how does this work? Well, we've got our undersea volcano and it erupts. And volcanoes tend to erupt, they get pressurized, they're full of gas, and you get an explosion going off. That's the extremely basic layman's terms of how a volcano works. And when it erupts in an explosive manner, you get this gas jet. So it's kind of in this cartoon, this dark gray area. And then you get this zone of more mixing where you don't get as much jetting going on. But you start to get some sort of buoyancy driven convective plumes. And in this case, the pumice, as I said, which are very vesicular, some of these vesicles can be closed off, full of gas. So they're very light and they'll float. And that's how you're going to get these pumice rafts. Whereas some of these more dense materials, which are in black in this cartoon, will sink back to the surface or to the surface of the ocean floor. Your pumice will eventually do that as well as they start to get waterlogged, but that can take weeks to months to actually happen. But you can also get kind of these pyroclastic currents that come down the sides as well. And eventually, if your volcano lives long enough and has enough eruptions, it might emerge from the ocean. And the most common type of eruptions for these are Circean eruptions. So you've got this volcano, it's creeping shallower and shallower, and eventually it gets shallow enough that one of these eruptions might breach the surface. So you can see here, one of the common features of these are these base surges at the bottom that go out laterally. You tend to get concentric waves associated with them, as well as this darker plume material with what's called cox-tailed tephra that are throwing up dense material that fall back into the ocean. So these tend to happen kind of episodically. You get an eruption, water fills back into the vent, water and hot magma don't like each other very much, and you can get another eruption that these can go on for, well, quite a long time. And now I'm going to move over to kind of the monitoring aspect, and I don't really have too much to say on this, just because monitoring submarine volcanoes is not as easy as subaerial volcanoes, as you might imagine, because, well, one, the seafloor is not mapped very well. You can see here just the difference in resolution from 1991 through 98 through 2010, and this is just a composite image. And this is just for one small section of the ocean floor. And even this composite image, compared to modern day LiDAR mapping techniques that we have for subaerial volcanoes, is not quite as nice. So one of the big problems with kind of monitoring is just mapping out a volcano, because we don't have the high resolution data for all of the ocean floor like we do for large parts of the land. Another problem comes in with monitoring. Some submarine volcanoes are monitored. Loihi, which I said was off the coast here of Hawaii, down off the south coast, used to have a seismometer. It does not anymore because it quit working. But you can see here in this image, they're putting in a seafloor seismometer and hydrophone. And Art can talk a lot more about these sorts of things than I can. But these things are kind of rare. They're expensive to put in. And for a single submarine volcano, you're probably not going to put more than one. Whereas you can see a comparison to the island of Hawaii here, and just how many seismometers, tilt meters, gas meters, GPS, camera there are to monitor just Mauna Loa and Kilauea themselves. So that's kind of the drawback of trying to work on submarine volcanoes as far as a hazards perspective goes, is that they're really hard to monitor, and mapping them is a lot more effort than it is on subaerial volcanoes. And I don't want to go too much more into that and steal any thunder from Natalia. So that is all I have for this very brief introduction to submarine volcanism.
Okay, thank you, Drew. And if anybody has questions, why don't we hold off till the end? Maybe write them down, and then we'll handle all questions then.
Okay, thank you much. And I will stop sharing and hand it over to Natalia.
Okay.
All right, can you see my screen in big format, or is it just showing the PowerPoint presentation? Is that better?
I'm seeing just your presentation.
Great, fantastic.
I think. Hold on a minute. Okay, now it's this resume slideshow.
Is it good now?
Now I see.
I resumed. All right, fantastic. Thank you.
Okay.
Great. Well, thank you for the opportunity to speak to you all. I see a couple of familiar names on the call, so hello. I'll be talking about subaerial submarine volcanic hazards. I know that's a bit of a mouthful, focusing more on the processes and the hazards, and then Art will dive more into the specifics of what happened earlier this year. I noticed during Drew's presentation that there was a question about having a map of volcanoes with the Pacific in the middle. So I quickly threw up this slide. This is from the inner cover of the Encyclopedia of Volcanoes. It's not showing what's submarine and what's not submarine, but it does show just how many volcanoes there are in the Pacific region. So everything that's a solid red triangle has erupted it's a dated eruption within the last 10,000 years. If it's not quite a solid triangle, a red outline, that means it probably erupted within the last 10,000 years. Then there's a few X's where it's uncertain. And then the different plate boundary types that Drew was referring to are also indicated. But so this is a Pacific-centric view of where the world's volcanoes are. We can see that we have a lot of volcanoes in this region. So for the next 15 minutes or so, I will be first talking about submarine volcanism, focusing specifically on ash, because I understand that is something that you might be dealing with. I'll then go over tsunamis that are generated by volcanic eruptions, focusing on the oceanic ones. And then this is unfortunately a very US focused slide, 2 slides, but there is a US national threat assessment of volcanoes, including some submarine ones. So I thought I would throw that in. That kind of assessment hasn't been undertaken systematically for the whole Pacific region, which is why I won't be showing that. So a lot of people are more familiar with so-called dry volcanic ash as opposed to wet. And this has nothing to do with whether or not it encounters rain once it's erupted. It really has to do with how it was formed, what kind of volcanism led to it. So dry ash would be an eruption that formed without much interaction from water, either be it ocean or lake or quite saturated groundwater. So dry ash or a dry eruption would be what we view as a more typical eruption. Whereas wet, there's a really strong influence of water in the eruptive processes. So volcanic ash is formed via magma fragmentation. So if you look at dry processes, and this is what most ash that we deal with is formed through these dry processes. There's really 2 ways to form ash. So yes, it's fragmentation, but how do you do that? One is you just really rapidly accelerate the magma as it's rising towards the surface, and the fragmentation occurs when the formation of the gas bubbles in the magma happens too quickly for the gas bubbles to really coalesce and for there to be permeable gas escape, and so they'll just fragment the bubbles. Rapid decompression is the other end member of how magma is formed in dry eruptions. And this would be, you just decompress it so quickly that nothing else is really that important. So bubble nucleation or growth, those are irrelevant. And in this case, the depressurization makes magma behave quite brittlely and it just shatters. So those are the end member processes of dry ash formation processes, which is usually what people deal with in volcanic eruptions. But if we then go on to wet magma fragmentation processes, you have some other processes involved as well. So you do have thermohydraulic explosions. So this is when you have really rapid heat exchange between water and magma with a sufficiently large contact area. Again, this has to be quite rapid. And so then you get this explosion. You can also get, this is actually how most of the ash is formed in wet processes. The shock wave that is caused by this explosion will pulverize rocks nearby. And so wet magma fragmentations has these additional processes to contend with. So the way ash is formed in dry and wet eruptions is a bit different. And as you might expect, the plumes, the resulting plumes can behave a bit differently as well. So dry eruptions versus wet eruptions do have a different profile in terms of how well they fragment, so how pulverized they get, and also where they go. So it's noted that often wet eruptions are quite poorly sorted, which means there's a big mix of fine and coarse grained material. And you also have very fine grained materials close to the vent. So usually when we think of a volcanic eruption, the finer stuff will go further, and the further you go, the finer the material. So there'll be some kind of sorting. Whereas for wet eruptions, usually there's a lot less sorting and you have much finer grained materials close to the vent. You also have increased generation of ash. Maybe this is because there's more ways to generate the ash, but compared to analogous eruptions that are dry, you do have increased ash production for most wet eruptions. And then finally, wet eruptions, there's water around, and so you do get wet aggregation of ash that can also quite rapidly remove fine-grained material from the atmosphere. So even though you have more fine-grained material, more of it is removed closer to the vent. So this is illustrated in this diagram, I don't think this is real data. This is more representations, but this is on the x-axis, you have a proxy for dispersal. So the area and how far ash is deposited, whereas F is a proxy for the efficiency of fragmentation. So how fine-grained is this material? Usually, people are dealing with dry eruptions. And that is illustrated here with the Hawaiian through Strombolian through subplinian and plinian. And this is actually what a lot of ash dispersal models are calibrated on or are meant to represent. You can see the Circean and Phreatoplinian. These are wet eruption types. Drew showed some examples of Circean eruptions. You can see that they don't plot on that trend that a lot of models are calibrated on. So they have way more, the F is much higher, so you have much finer grained material. But despite how fine grained that material is, the dispersion coefficient is a lot lower. So this just speaks to the processes are a bit different. And so while models, all models are wrong, but you want useful ones, the models that are used for ash modeling are usually quite good, but they are calibrated for that. So if you see a mismatch in your operations when you're dealing with a wet eruption, this could be one of the explanations why. One thing to note is that this plot here, you can see the proportion of fine-grained material is quite high for Circean and Phreatoplinian. This is based on people generally, this is based on people sieving the ash to get at grain size distributions. But in a lot of traditional methods for doing this, you actually break up whatever aggregation there might be. So even though wet ash might aggregate, it won't be captured in a plot like this because it's really looking at the base fragmentation material. So that's one reason why these plot quite differently, although reality might indicate that F might be a little bit lower if you're thinking about gravitational settling parameters. Hope that makes some sense. I see the question from Lily about ash, long-term impacts. I'll touch on that at the very end, so please remind me if I haven't. So those are my 2 slides on ash, but I do want to make a brief point about leaves, and this is outside my area of expertise, but it's something to, at least when we're dealing with subaerial volcanoes, then this is something we see when it encounters seawater, when you have lava and seawater interacting. So I would assume this could be an issue as well with very shallow water or even submarine eruptions that break the surface. So LAYS is short for lava haze, and it forms when lava enters the ocean. And there's that interaction with seawater, creating a steam plume that has hydrochloric acid. Again, the interaction with the seawater, salt is a very important component, and often fine glassy particles. So this is nasty to breathe because both chemically and physically is very unpleasant. So you can have this additional hazard of LAYS formation when you have lava and seawater interacting. The amount of exposure someone might get would depend on the amount of lava and seawater interaction, as well as where the wind is blowing this plume. I'm not going to talk about volcanic tsunamis. So the most generic definition of tsunami I could find is a long period water waves generated by a sudden displacement of the water surface. And while most people think about earthquakes generating tsunamis, volcanoes do generate tsunamis as well. So there's a couple of ways volcanoes can generate tsunamis. They can generate them through eruptive processes, through intrusive processes. So that's when you have the injection of magma underneath the surface, causing rapid ground deformation, and also gravitational. I was very surprised to read this, but according to a study by Parasol in 2013, about 5% of all tsunamis in the last 400 years are volcanic tsunamis. So it's a non-trivial percentage. And if we put on the volcanologist lens on, about a quarter of fatalities attributed to volcanoes in the last 250 years are actually caused by volcanic tsunamis. So from a volcanology point of view, these are very concerning. This cartoon here shows the main mechanisms by which we can generate a tsunami by volcanic processes. And I'll be going into these in more detail. You will see this figure again a few times. So this is just a small selection of some documented tsunamis within the last 200-ish years. So this just goes to show that there's a lot of documentation about these, and they can cover all parts of the world. So what we have here is the location, so the volcano it's from, the year it's from, the kind of volcano it is, what caused it. So this goes back to that cartoon I showed you on the previous slide, which you will see again. The max run-up, how far these traveled, and the number of fatalities. So there isn't always a correlation between the max run-up height and the number of fatalities, but you can see that some of these can be quite lethal, and they can also travel quite far. They're perhaps a little bit more localized on the whole than some of the large seismic caused tsunamis, but they can still have quite a big footprint. The volcano types, you will notice that a lot of these are quite near the ocean or in the ocean or completely submerged in the ocean. Those are the kinds of volcanoes that make tsunamis. And the causes can be quite varied. So it can be submarine explosions, it could be the entry of volcanic hazards into the sea. It could be a big landslide, so that's what the debris avalanche is. There's a number of causes that can trigger these. So I'm going to go into 4 of these in just slightly more detail. Looking first at a shallow submarine eruption, then a large explosive eruptions. And while I'll be focusing on Krakatau, that David really nicely introduced, this is what happened in January of this year. I'll look at volcano landslides and debris avalanches, and then the most unusual one that I found quite surprising, but it has been documented, is the sudden ground deformation associated with volcanic eruptions causing a tsunami. So let's start with Myojin-sho in the Izu Islands off the coast of Japan. So this is a quite shallow submarine volcano. And in 1952 to 1953, just over a year, it had over 1,000 phreatomagnetic eruptions. This is not an alarming number of eruptions when you have an active volcano. As Drew mentioned, you can have lots of back and forth explosions. So explosion, things calm down a little bit, then seawater goes back in, another explosion, and so forth. So this is a big number, but it's not a weird number for this kind of activity. What is quite sad about this eruption is that a bit after the eruption started, there's a Japanese survey ship that was pretty much right over the volcano when it erupted, and that ship and everyone aboard was lost. That explosion that took the ship did cause nearly a meter tsunami, arriving about half an hour later, a bit north of it. So on the map on the right there, I pointed an arrow to where the volcano is. And if you go 2 solid dots to the north, that's where that arrival was half an hour later. So over quite a short period, 2 weeks in March 1953, there were over 50 tsunami recorded. None of these were huge, but it's just to show that, this can be quite a real thing. And just based on the longevity of this eruption, how many explosions there were, and this observation over this 2-week period, likely there were hundreds of volcano tsunamis generated over the course of this eruption. What was very interesting to me is that a paper that was published in 1954 contains, I couldn't find the original source material, so apologies for that. but it describes the formation of a tsunami wave. So according to this person, and I note it's the day before this ship was lost, so I don't know what the situation is with that. But according to this observer, the water above the volcano swelled into a dome 5 meters high and 200 meters wide. Instantly, water began to fall outward from the dome like a waterfall. Then the central part of the water dome was pushed up into a serrated form to a height from 30 to 60 meters. A black mass of volcanic debris protruded from the water mass, and in an instant, the water and black mass became one. Intense noise and air concussions took place during the explosion. So that's describing a phreatomagmatic eruption that is also generating a tsunami. Now I'm going to move on to Krakatoa, 1883. This is a large explosive eruption. It's the second largest eruption since 1800, so it's bigger than the two largest eruptions of the 20th century, which is Katmai and Pinatubo. So this is a very, very big eruption. And the table that I have on the left, that shows different ways that you can generate a volcano tsunami. And the darker the color means, the more this is really a factor in this, whatever that example was. And here you can see that there's a lot of factors contributing to the generation of a tsunami. So on the right, I have a map of Krakatoa, and the blue lines emanating from it show the 10-minute travel distance contour lines. So just shows how quickly it moved. The scale bar is all the way on the top right. There's a 10-kilometer scale bar if you're not as familiar with this region. So this was a marine caldera forming eruption. This is a very, very, very big eruption, much bigger than the Tonga eruption in January. And it was heard 400 kilometers away. So there were several tsunamis associated with the eruption. An eruption like this isn't just a one-shot event. It will happen over several days. Yes, there is a main event, but there's a whole lead up to that finale. And so there were several tsunamis in the lead up to the big one, but the biggest tsunami, which coincides with the biggest energetic part of this eruption, that was likely caused by pyroclastic density currents entering the ocean, and it killed over 30,000 people along the shores. So quite devastating. If we stay at the same volcano, so it blew itself up in 1883, and something that often happens after an eruption like that is you'll get a resurgent dome in the middle, a little volcano emerging from the remnants. And this is Anak Krakatoa, which means child of Krakatoa. So it first appeared about 50 years after the 1883 eruption. And in December 2018, a large part of this volcano just slid away, it collapsed. So on the upper right there, there's a map. The blue line shows the shoreline before this collapse. And then everything in gray survived the collapse, but everything else is gone. Yeah, I think I have that the right way around. But so half of the subaerial extent disappeared, and this big landslide generated tsunami, unfortunately, during high tide. So that exacerbated the problem. The tsunami reached the coast in half an hour. 437 people were killed, 13,000 injured, and 33,000 displaced. The map here in blue, it shows the affected areas. You can see that it covered quite a large region. And while the numbers are a bit on the small side, the highest run up was 13 meters. So this carried quite a punch. The two photos on the bottom show what the area looked like before and after. And before, you'll see this orange glow, and it's kind of illuminating a profile that looks like a little triangle. And then, so that's Anak Krakatoa before, and you can see there's a tiny little pinprick of glow afterwards, but that nice profile is gone. this landslide took a lot of the island away. So this final case study, this is a weird one. This is not common, but it happened. So we're going to go all the way to Italy now. The Vesuvius 1631 eruption. This is the largest eruption since the so-called Pompeii eruption. And during this eruption, the third and the largest phase of the eruption started with quite a big earthquake. I don't know what the magnitude was, but it was about 5 minutes long. So you can imagine that's a pretty big earthquake. And what's interesting is that the ocean gradually withdrew hundreds of meters and then suddenly came back, so tsunami, at the same time as some pyroclastic density currents were emanating in this quite remarkable print. You can see those brown rivers that are emanating from the volcano. That would be a pyroclastic density current. So the tsunami was concurrent to the pyroclastic density currents. They were not caused, the tsunami was not caused by the pyroclastic density current. So one hypothesis for how this happened is that as magma was approaching the surface, you had overpressure that led to really rapid deformation. And then once the cap went off and the eruption started, you had very rapid subsidence back to its original position. There were 3 damaging waves associated with the tsunami with 2 to 5 meters run up. And all I could find is that it destroyed many boats, but this eruption was quite problematic for the Naples region for everyone on land. Not necessarily because of the tsunami. The tsunami was not a huge factor or any factor in loss of life, I'm not sure. But it's just interesting that this is a completely subaerial volcano, and yet it could still have a tsunami with the ocean. Something I have not covered in these case studies is the acknowledgement that you can have tsunamis generated by volcanoes in lakes. But since we're focusing on the Pacific region and Pacific Ocean, I decided to omit discussion of that. But you can have tsunamis formed in lakes by volcanoes. So I promised you would see this cartoon again. So you can form volcano tsunamis by a variety of different mechanisms. All that's required is the rapid large displacement of water, as we know, and about 5% of tsunamis in the last 400 years are volcanic tsunamis, at least according to databases. And yes, there's many volcanic tsunamis and non-volcanic tsunamis that are likely missing from that. And when there's large loss of life from volcanic eruptions, volcano tsunamis certainly contribute to that figure. I now have 2 slides. This is US centric, so apologies for that. But the USGS has published a national volcanic threat assessment. The last update was in 2018. And this allocates volcanoes or categorizes them into very high threat all the way to very low. And the assessment consideration considers things both related to the volcano and then to the exposure around that volcano. So volcano considerations include the type of volcano, how big eruptions could be or likely to be, how often these occur, the types of hazards, and what has been observed in documented time. And then the exposure has to do with population, aviation, and then infrastructure and other considerations. And also if the volcano is pretty much the entire island, if it's an island volcano, that also ups the threat level because evacuation becomes quite a bit more challenging. So just as this was done for all US volcanoes, here I'm just showing the US areas in the Pacific Ocean that have volcanoes. To zoom in on these, this is looking, we have the Commonwealth of the Northern Mariana Islands on the left, Hawaii on the upper right, and then American Samoa on the lower right. Again, the colors correspond to the threat assessment, and I've taken the liberty of underlining all the submarine volcanoes that are shown here. There's a lot of volcanoes that are missing. So the volcano formerly known as Loihi is deemed too deep by the person who generated this report to warrant mention in this assessment. And there's undoubtedly a lot of other volcanoes that are omitted from this assessment because they're deemed to be too deep to really be to pose a threat. But there are submarine volcanoes that even go as high as a moderate assessment. So to recap, briefly talked about ash characteristics of submarine volcanism, highlighted tsunamis, and then looked at the threat assessment. I'm now quickly going to answer the question about ash impacts. So it looks like Drew did a good job of answering that, but certainly ash can cause quite a bit of headaches, and more than headaches for people living nearby. When ash is wet, it is a lot heavier, and so that can increase load if the structural load is one of the damaging characteristics, for example, in buildings. It can also become a lot more like cement quite quickly, and so that can cause additional headaches. So yes, ash can affect all aspects of life. It can affect habitability of buildings, or even whether or not you have a building. It can certainly be problematic for agricultural lands, especially depending on the time of year. But if you have enough ash, the time of year doesn't matter too much. And certainly roadways can become much harder to use when there is ash, whether it's dry or wet. Do I have any other questions? Doesn't look like it. Nice to see you, Emily. So I think with that, because we're holding questions to the end, I will pass it on to Art. If I can figure out how to stop sharing.
Thank you, Natalia. Can everyone hear me?
Yes.
Okay. Let me see if I can share the screen. And that. Can everyone see that?
No, I do not see your slides yet. There we go.
You can see?
Yes.
Okay, let me try to get it full screen here. There we go. And okay, thank you all for having me. My name's Art Jolly. I'm with the Hawaiian Volcano Observatory, formerly at GNS Science in New Zealand. I'm going to talk to you today about mainly about the aeroacoustic observations of the January 15, 2022 eruption in Tonga. And I'm going to talk about eruption dynamics and global acoustic wave propagation. This is really a remarkable eruption. And I hope that when you leave this presentation, you'll get a sense of some of the remarkable aspects of that event. Oh, I've also, before I go forward, this talk has contributions from several people. It includes contributions from NZBSAP folks in New Zealand, USGS PDAP team, and I'm on Seismic and Infrasound Science Working Group. And that working group, the latter working group, they have a manuscript in consideration. And as a result, there's a fair amount of really nice material that's embargoed. And so that none of that information is going to be in this talk, but it's I will allude to it in this talk and show you some examples. That's quite a remarkable manuscript that's in preparation. So the basic outcomes that I want to talk about in this particular talk include these three aspects of that eruption. First off, the eruption was exceptionally large in terms of its eruption column. And it's actually probably in terms of eruption column height, It's thought to be the highest or biggest eruption in terms of column height at 58 kilometers. And that's quite large compared to the actual erupted volume, which the last estimates I heard was on the order of 0.3 to 0.5 cubic kilometers. Put that in context, Mount St. Helens eruption was on the order of 1 cubic kilometer, so larger than this eruption in terms of volume, but much smaller in terms of ash column height. And that's really an enigma in terms of this event, and we'll discuss some aspects of that going forward. It also produced, because I think it had this exceptional exceptional ash and steam column, exceptional atmospheric wave propagation. And when you see some of the examples of the atmospheric wave propagation, those are almost equivalent, or in some cases exceeding the recorded pressure waves associated with the Krakatoa eruption. So really a remarkable event from this eruption compared to that. I'll also talk a little bit about the unusual tsunami wave propagation that occurred in that event. And so Natalia's beautiful talk will have is a nice segue into that discussion. So the eruption itself occurred in January 15th. That eruption actually occurred, the onset of that eruption, the eruption episode began on December 19th, just before Christmas 2021. The main eruption started on January 15th, and the first eruption plume was visible in the GOES satellite, GOES 17 satellite at 4:06 UTC. All these times are in UTC, and that is basically 11 hours behind the time frame for the eruption. No, it's 23 hours behind Tonga. I'm sorry. So it's about 5:06 Tonga time. There were a series of small earthquakes and volcanic lightning that was observed in these small eruptions that occurred prior to the main climactic onset of eruption, which was at 4:15. And that was synchronized with this largest earthquake that occurred, which was magnitude 5.8, which isn't that large of an earthquake, but it was the largest earthquake in a sequence of earthquakes that occurred at this volcanic center. And to let you know, there's very few observations in the near field of this volcano. Most of the observations are regional distance. And so you rely on regional and global scale acoustic and seismic observations for this particular eruption. These figures are provided by Shane Cronin, and he and his team were out there, I believe, in 2015, looking at observations in 2014 for the eruption that occurred during that time period. And that eruption produced this Tephra Island that connected two small islets, Hungatonga and Hungahapai, back in that time period, about 5 years before. So the eruption produced this very large eruption and huge ash cloud. The eruption persisted for a couple of hours at very strong duration. It also produced these it cut the cables of the main telecommunication lines that were underlying the volcano. And the domestic cable was cut about 5:30 p.m. local time. And then the international cable was cut about 5:44. So this is on the order of an hour and a half after the eruption, or 15 minutes to an hour and a half after the main eruption. Now, one of the concepts that people were talking about initially was, did the eruption, was it produced by a unloading or a collapse of the island structure? And this would suggest that the main eruption actually preceded those cut cables. And so that would suggest that if there was some kind of subsurface avalanche deposit that cut the telecommunication fiber cables, it happened after the main event. So that's kind of the chronology of this particular eruption. If we go on to the Tonga eruption, some of the observations, one of the things that I've already mentioned is that this eruption produced globally propagating sounds, so acoustic waves. And this shows a wave train from two acoustic stations, located here in Hawaii. And it shows both low frequency signals and high frequency signals. And you'll probably have heard that this eruption produced not only infrasonic observations, but also acoustic observations. Here in Hawaii, there wasn't acoustic observations, but as you went further north to Alaska, there were wide-ranging acoustic audible sounds associated with this eruption. So I'm going to talk to you about how this happens, how you produce infrasound observations that propagate so far that they travel around the globe, not only once, but several times. So we need to, in order to understand this, we need to understand something about the eruption dynamics. And when I talk about eruption dynamics, I mean the acoustic signals that are produced from ash being flung into the air. And this is really a process of mass flow from the volcano, either vertically as an eruption column or laterally as a pyroclastic density current. And then you not only have that eruption, the eruption dynamics, but then you have wave field propagation. And this is the acoustic waves that are associated with this mass flow. That could be supersonic mass flow or subsonic mass flow. And this shows a neighboring island of Vanuatu. This is Yasur. And this just shows a small strombolian eruption that's directed and produces this mass flow that is then can be recorded, in this case, locally at that particular volcano. But then the wave field propagates outward from that, and it is either diffracted around topographic features or refracted if this propagates through the earth and different velocity structures occur. And then you observe that on different types of observation sensors, barometers, or acoustic sensors, or microphones. Oopsie. So the source process is actually somewhat complex, but understandable. And in terms of just the eruption itself and this initial process of mass exiting a volcanic vent, these things have been studied by acoustic scientists like Lighthill and Wolf and McKetchin, etc. And they describe these things in terms of monopoles, dipoles, or multipoles. And a monopole is basically kind of what you would think of in terms of an explosion. This thing radiates in all directions in the same way, the same amplitude, and it just propagates away from that source. A dipole is basically where you have eruption and it excites two poles that are phase lagged by 180 degrees. And you can have multipoles that are offset from dipoles, and they can be more complex. And all these things can be modeled as part of an acoustic wave field at the near source. And this is requires that this is a compact source. But we have to be careful here, because if you have plume propagation effects, they're likely to be significantly important. And you can imagine from our previous slide showing this eruption column and plume from Tonga, that you have this large lateral plume, and you have a buoyant umbrella cloud that propagates laterally from this. And those are going to be sources of acoustic wave propagation in and of themselves. And so these extended sources, they produce features like jet turbulence and buoyancy effects that can be measured on these surrounding acoustic sensors that may be measured globally. So I'm going to go through a little analog, and this analog is in the ocean, and propagation of ocean waves, which are acoustic waves just like the atmosphere, but it has properties that are somewhat different. And this shows some data from a paper by Metz in 2016, and it's a volcano called Manawai, which Manawai is in the Kermadec Arc in the South Pacific. And it's actually monitored day to day by the New Zealand GeoNet project. And they monitor that volcano at a station in Rarotonga, which is a seismic station, which picks up these converted seismic waves that are from the eruption that propagates in the ocean. And it turns out that these waves can actually propagate incredibly long distances. And this data here by Metz is actually in Ascension Island, which is in the mid-Atlantic. So Pacific Island volcano produces acoustic waves that can propagate thousands of kilometers all the way to the mid-Atlantic. This shows where the Ascension Islands are, and this is shows an array of acoustic sensors, or hydroacoustic sensors that are located about 1,000 meters depth off of Ascension Island. And they actually recorded those signals that you saw in the previous figure. We go back, this shows the amplitude of the signal, the correlation coefficient, which is the coherence of the signal on all these different stations that are around Ascension Island. And this shows the back azimuth, which organizes around 210 degrees azimuth, which basically points southwest towards the gap down here at about 60 degrees south. And so this is propagating along the SOFAR channel, the so-called SOFAR channel, producing these waves that are observed several thousand kilometers away. So how does this happen? And this is basically a product of hydroacoustic ducting. And the ocean basically has acoustic velocity or sound speed, which is dictated by the depth and by the temperature, which is changes fairly rapidly in the first few hundred meters below the surface due to heating from the sun in the upper layer of the ocean. But then oceanic pressure takes over, and that increases the sound speed as you go deeper and deeper and deeper. And the lowest velocities are right here at about 800 meters depth. And that's what produces the SOFAR channel. And wave propagation loves these low velocity layers because it can cause incident seismic or acoustic waves to propagate along and get trapped in this low velocity channel and then propagate with very little transmission loss of that wavelet. So it can propagate through the earth massive distances without being attenuated. It turns out that this same feature that we see in the SOFAR channel is also seen in the atmosphere, but it's a much more complex system because you have various layers in the atmosphere. And this is a plot in a paper by David Fee and Robin Matosa, who are colleagues of mine. And they have done a lot of work on global infrasound. And they did this analysis at Mount St. Helens, where you have basically the layers of the troposphere, and they look at the velocity structure of the Earth around above Mount St. Helens. And it turns out that that has this, this rather complex pattern of velocity structure with elevation. And this is also associated with the temperature of the waves, or the temperature of this profile. I'm sorry. And if you look at this layered structure, it also has some additional complexity. And this additional complexity is associated with the wind. And you can imagine if you're flying along in an airplane, that you have jet stream wind in the upper stratosphere or in the stratosphere, and these are quite significant. And they cause the change in the sound speed and can produce waveguides in the atmosphere, just like they occur in the SOFAR channel in the ocean. This shows a really beautiful plot that shows ray tracing through this empirical atmospheric velocity model that David Fee and Robin Matosa did. And what it shows is that there are these waveguides that are occurring at different levels in the atmosphere. It shows that one occurs at about 10 kilometers, below 10 kilometers depth in the troposphere, in the stratosphere at about 45 kilometers depth, and then the mesosphere very high. And these waveguides, just like the waveguides in the ocean, are very efficient at propagating acoustic waves, but it depends on the direction that you're traveling. This shows that if you're traveling in the direction of the wind, you can propagate in a waveguide very efficiently. But if you're propagating in the direction of the wind, it is actually very inefficient, and waves don't propagate nearly as efficiently. So if we go and look at some barometric observations and pressure sensor observations from various points around the Earth, we get a sense of what's going on. This is the closest barometric observation. It's data courtesy from some people in Australia, Greenwood and Aquilina, and the image was produced by Matt Haney, who's a colleague of mine in Alaska. And this shows that you have this big overpressure that are associated with the onset of that volcanic eruption, and you have this wave that occurs and it propagates along after that eruption. And it shows basically when the onset of this eruption occurred. If we go down to New Zealand, which is about 2,000 kilometers away, we see that, that the acoustic waves are propagating there also. They have very low frequencies, but they have some high frequencies associated with them. And this shows that an array that's actually used for monitoring the volcanoes in New Zealand, that array has captured those signals from the Tonga eruption. Further away still, we have observations about 5,000 kilometers away here in Hawaii. And we see that we have signals that are still in the infrasound range. So below the audible range where you can actually hear these things, but they're still recordable from infrasound sensors like we have in HVO. And this is a figure courtesy of Milton Garces that shows some standard smartphones that he has set up in his infrasound lab that also recorded these sensors, or recorded this event, I'm sorry. So we're coming towards the end of this thing. And I wanted to mention this really lovely paper by Horace Lamb, and he's one of my heroes. He was back at the turn of the last century He did a lot of formative work, not only in hydroacoustics, but aeroacoustics. And he did some of this first work on what are called atmospheric gravity waves, which are similar to the tsunami wave propagation that occurs in the oceans. And I want to point out in his paper on atmospheric oscillations, which was published in 1910, that basically acoustic gravity waves, when you think about a column with a layer structure, basically they can be treated as a wave that is driven by the gravity. And this, if you look at that equation there, G times H, which H is the height of this column, that's the same propagation velocity, or that's the same equation, I'm sorry, as tsunami wave propagation, but it's in the acoustic wave field. And so I'm going to close out the talk with a discussion of tsunami waves. And in the tsunami wave field, we see this particular figure, and it's been produced by Guzman and Roger, some colleagues at GNS Science. And they show this acoustic propagation, tsunami wave propagation. I'm sorry, I'm mixing my terms here. Tsunami wave propagation and some dart buoys that are surrounding New Zealand. And you can see here the blue is a simulation of what the tsunami wave would be if it's just propagating along the ocean surface at tsunami wave propagation speeds. But you can see the red is the actual data recorded on those dart buoys. And you can see here in several examples that the observed tsunami wave occurred several tens of minutes before the actual simulation of the tsunami wave. And why is that? Well, if we go back to this paper by Horace Lamb, and we look at and plug in the theoretical propagation of a tsunami gravity wave, they propagated about 800 kilometers per hour. This is about the velocity of an airplane or a jetliner. But if we look at this in context of Horace Lamb's acoustic gravity wave, they propagate at about 1,100 kilometers per hour. So modestly faster than a tsunami wave would propagate. And what is going on here is that you have this acoustic wave propagating away from this eruption plume, and it's propagating faster, and it's putting this acoustic pressure into the ocean and producing this pre-tsunami wave that's being recorded on these dart buoys. And I listened to a talk recently by Emil Okal, who's an eminent seismologist, and he showed that this actually occurred not only in the Pacific Basin, but in the Mediterranean and in the Atlantic. And so what he said was, effectively, when the acoustic wave propagates over the land, then it stops in terms of its interaction with ocean. But then when it goes back over the ocean, then it reestablishes that acoustic gravity wave, and that then propagates and produces effectively a new tsunami wave that's propagating at acoustic gravity wave velocities. So I'm just gonna close out with the same basic outcomes that we came from the start. We had this exceptionally large eruption column, which is about 58 kilometers in height. And this is actually at the height of the theoretical limit of plume heights. So incredibly high column. It produced an exceptional atmospheric wave propagation. And that atmospheric wave propagation actually coupled back into the seismic waves or into the ground, producing seismic waves, but it also coupled into the ocean, producing what look like tsunami waves. And this unusual tsunami wave propagation has implications for tsunami hazard globally. And so I'll end on that, and thank you very much.
Okay, thank you, Art. The stuff on aeroacoustic waves is fascinating to me, and hydro acoustic waves. Okay, so we have a lot of questions. I want to make sure that I address all of them. So Eleanor, who is the MIC in Samoa, was asking about how the ash cloud affects the climate. So I guess I mentioned with Krakatoa that for the next year it affects, I read different figures between 0.3 C and 1 C cooling of the general Earth atmosphere over the year. But how does the ash work, and what is expected, I guess, maybe from the Tonga eruption?
So I think that's a question for maybe Natalia or Drew, really. That's on the edge of my experience level.
So I've answered a little bit in the chat. This is Natalia. While this eruption is exceptionally high, the amount of ash that has been put into the atmosphere is lower than some of the other eruptions that we know have perturbed the climate. So based on my very limited expertise, I would be surprised if there was a climatic impact of note. But the climate does rebound within a couple of years when there is a perturbation on the scale that we've seen in the last 200 some years. So the only eruptions I'm aware of that really perturbed the climate are Pinatubo in 1991, I think, Krakatoa in 1883, and Tambora in 1815. So that's not many eruptions. I hope that answered the question.
Okay. And then Robert Haukare, just to clarify, what type of eruption was the Tongan one? And also, I mean, I guess one of my points I was going to make in general is there somewhere we can source a glossary? There seems to be like a lot. Even I find it a little difficult with. There's a lot of jargon that you guys have in volcanology that I'm not even familiar with. So a glossary for everybody if that exists somewhere on the web, that would be useful to know about.
I'll drop a link in the chat to a glossary by the USGS and also one by GNS Science in New Zealand.
Okay.
But the focus of these are what people living on land with an eruption in their backyard might be focused on. It's not so much submarine volcanism, but there's quite a bit of overlap, and I do appreciate we're very jargony, so big apologies about that.
That's just how it is. Did Emily's question get answered? Sorry, I was paying attention to Art's talk and I wasn't fielding the chat. Emily, if you're there, did you get?
No, I haven't heard yet. Do you want me to basically ask what it was?
Yeah, please do.
Yeah, no, so I'm sort of super interested in the fact that, okay, you can measure these earthquakes, in inverted commas, from the volcano. And I was just sort of wondering whether you can actually work out what part of the volcanic eruption is causing these separate earthquakes. Like, I mean, is it things like caldera collapse or magma movement? And I was just wondering whether, those sort of beach ball source mechanism things that you get from earthquakes, can you work out from that something about what might cause individual earthquakes?
So one of the problems in Tonga is that the nearest seismometer is I think, a couple of 100 kilometers away, if I know correctly. I think it's up in Fiji. And that is too far really to draw very good conclusions about source processes associated with that eruption. I think that there will be some study from that sequence to learn more. And I think there is stuff that can be learned about using that regional distance data. But it's not like Hawaii, where we have 100 seismic stations surrounding our volcano, or not quite 100, but several dozen seismic stations surrounding our volcanoes.
Okay, so my understanding is that with an above water volcano, you can set up sensors all around it, but with the underwater volcano, there's not the same sort of opportunities for observation.
Yeah, as Drew noted, it's inordinately more expensive to put seismic sensors on the ocean bottom. It is possible, but it's an expensive proposition.
Okay. Does anybody else have any questions? You can just open your mic if you'd like. Okay.
So sort of, sorry, following on from, are there any, I mean, I'm really interested in sort of, from a tsunami point of view, and I mean, the fact that you've got these multiple mechanisms, and so you actually might get multiple, smaller tsunamis within it caused by different mechanisms. And is there any way of working out from the observations that we do have things like when there might have been the caldera collapse, when there might have been a pyroclastic density current? I mean, I realize the answer might be no, but I'm just sort of curious as to your thoughts. Will we ever sort of pick apart these different parts?
So I think that Natalia and Drew might have some insights into this. I do understand from the New Zealand scientists that there's a hope of doing a bathymetric survey, so looking at the subsurface topography, and that has been done in the past, and a resurvey would tell us a lot about if there was a caldera collapse, where was material remobilized in subsurface, and I think that could be a remarkable study that will answer a lot of those questions that you're posing.
I'll just chime in and say that while I can't speak to the eruption earlier this year, there was some very nice modeling work done on the tsunami that I talked about at Ana Krakatau in 2018. And by looking at arrival times, various gauges around the volcano, they were able to fairly conclusively say it was a landslide rather than pyroclastic density currents or other mechanisms. So if you have a dense network of gauges, it certainly has been helpful to reconstruct what has happened. But again, I don't really know much about the availability of data on this one.
No, thanks, Art and Natalia. Yeah, I mean, we're sort of trying to piece it together exactly that sort of way, and sort of looking back and seeing when things might have happened. But yeah, we're sort of trying to see whether we can tie that in with volcanic observations as well.
Okay. I'm not sure I see any more. Oh. Okay, so I'm just going to ask one more question, and this is for me and my comrades in Guam. So there are several volcanoes north of Guam. I think Pagan, Natahan, I think these are all active. So what kind of, do these volcanoes pose a threat in the same way that the Tongan volcanoes do, or are they more benign?
So those are volcanoes in the Marianas, and they do feature in the National Volcanic Threat Assessment. So I can quickly re-show the slide if you wish. So these are volcanoes in the Marianas. Pagan is right here. This has been erupting on and off within the last year, from what I understand. All the ones that are underlined are underwater volcanoes, but a lot of them have been ranked as very low. My suspicion is because whatever eruptive record is available will probably point to fairly infrequent eruptions, but again, the record can be quite spotty, as Drew mentioned, for submarine volcanoes. So yes, there are volcanoes in the Marianas. Yes, they have erupted quite recently, some of them. But at least as of 2018, the USGS threat assessment is quite low, and that assessment does consider aviation, which would necessitate eruption columns that go quite high into the atmosphere. So hopefully that answers your question.
Okay. I guess what I was getting at is, do they have the same sort of explosive potential? Could they create tsunamis that could affect the Marianas?
Yeah, so, go ahead, Natalia.
Go ahead. No, go ahead, Drew.
I was just gonna say, so we do have a colleague here at the Hawaiian Volcano Observatory, Frank Truesdale, who's done a lot of work on Pagan. And it does have some kind of small scale explosive features, much like kind of the recent Tonga eruption though. The recent activity at Pagan does sit in a larger caldera. The problem is, I think that not enough work has been done to constrain the age as to kind of what's the recurrence interval between background volcanism out of the cone in the center of Pagan versus kind of what's the recurrence interval for kind of a caldera collapse event in the Marianas. But yes, certainly large scale caldera features are present in the Marianas Islands.
Okay, and then one last question. In hindsight, was the Tonga eruption expected?
I think it's hard to know if you had more dense observation. I suspect you would have if you had more seismic sensors, etc. You would get a clearer picture. But and forecasting is a big part of the game in volcano monitoring. But it's hard to know in retrospect if something like that would be, if you could actually do anything with that data. It's one of those questions that retrospectively it's difficult to answer the question.
Okay, all right. Well, thank you, Art. Thank you, Natalia. Thank you, Drew. And I'm going to close out the meeting there. So that thank you again for everybody for participating. I really enjoyed doing this webinar. Okay, so we'll see you next time in April.
Aloha, thank you. Bye-bye.
Thank you much.
Yeah, thank you.